This is a developer's introduction to machine learning, and giving a practical insight on how to get started today. Okay, so a few things that we'll touch on. I'm not sure if we'll be able to go through all of them, but I will touch on each one, hopefully. We'll go into data science, because fundamentally machine learning is totally useless without some data science, without some understanding of statistics or business value. Then we'll touch on the assessment of suitable technologies. Many of us work in enterprises, startups, small groups, maybe work in a huge corporate environment. And the applications of machine learning are very, very different for each group. So it's important, I think, to touch on those. We'll also touch on the types of machine learning. So hopefully with a bit of context, it should be much easier for you guys to find some relevance in your own data. And know exactly what you need to start with to start getting some value back immediately. Because there's no point in trying to build a calculator when you have absolutely no need for one, and you just won't have the enthusiasm or creativity to get the results you want. So hopefully some context will help. Then we'll do some case studies, which will give you the context, hopefully. I don't know if I'll touch on neural networks. That's a whole other talk entirely. But I will explain what it is and how machine learning is a huge part of that. I was going to do a practical demonstration. I don't know if there's time for this, but I will provide you loads of learning resources to help you get started on your own. And my contact details will be at the end. So if you do run into any stumps, then hopefully I can assist you. And horizontal scaling. So that's really when you start thinking about enterprise, or maybe your little data set suddenly grew from a few terabytes to a few petabytes, and the horizontal scaling solutions are something that are worth keeping in mind, even when you begin any machine learning endeavor in the first place, just in case you haven't thought about limitations later. Okay, then there is no code giveaway. Sorry, I should have removed that, but never mind. And then we'll have time for some Q&A, hopefully at the end. Okay, so this is me. I'm Arik Freeman. I'm a software solutions architect at a company called Automation Squared, where we primarily deal with prototypes and help startups gain funding, or look for grants or pioneer in technology. Software is difficult to be innovative in, if I'm honest. But we do loads of hardware integration stuff as well. So if you've got an idea for a cool new app or physical product, for example, we can help you spec that out and build it, gain funding for it, throw you through an accelerator, for example, which will make or break you within a couple of years. So we do all that fun stuff, and I particularly have, I suppose, a passion for the IoT, which is becoming a huge industry, or has been in the last couple of years, and machine learning is really very applicable to the IoT. Which is why I have such great experience with it. So hopefully a couple of the examples that I'll bring up will be actually real life projects that we've been working on in the last 6 months that are really, I think, really awesome, and should extend some really good context to you guys. Okay, but otherwise I'm a full stack web developer, or have been for the best part of 15 years. I've been recently in app development, so native app building, Swift, Objective-C, and Java. I suppose my original entry into this field was through mechanical and manufacturing engineering. We needed a little program for CNC, and it just kept going. Anyway, I also have I suppose an affinity to RTC and WebSockets, because they really do help with machine learning or artificial intelligence in general. Because without real-time communications, you have poor latency, which really does extend time and the value of your operation. So that does come in handy, and I will put some learning resources to RTC stuff as well. So it's a bit of a spin-off of machine learning, but it is the value in that is enormous. And anyway, yeah, so that's me. I wanted to highlight some data science and where machine learning sits with that. I think that little picture on the side here is perfect, really. Most of us are probably in the software development space, where we we can type stuff on keyboards, and we think we know a little bit about business. So I think that's most of us. And machine learning is a tough one because without a strong background in not necessarily maths, I have to admit, but yes, maths and a lot of statistics. A lot of the time, you have your Texas Instruments calculators, if you remember those in high school. A lot of the functionality is built in, but it's very manual with a calculator. But machine learning tries to, I suppose, elaborate on the power available to you through statistics. So without statistics, you haven't got the vocabulary to express yourself with data, should I say. So the more you know about statistics, I believe anyway, the more you're able to come up with creative ways to use machine learning to get awesome results. So that is something that I do want to stress, is a lot of getting into machine learning is, yes, if you're a software developer or a programmer or have some understanding of computer science, then you're on the right path. But if you've got no fundamentals in statistics, you're going to find it very hard to come up with good solutions. So statistics are a tool set effectively, and loads of academics have come together and put together really awesome little packages to help computer science guys to get the most out of their data. So hopefully I'll be able to show you how to get started with this immediately towards the end of this. Anyway, so business value from data. This is there is no point undertaking a machine learning operation without there being any value in it. A lot of it is for exploration. I totally agree, but much like innovation, it is costly, and a lot of the time your boss doesn't want to pay you to sit in your office for 2 weeks and play with data. So you've really got to have an objective, a goal, and maybe some idea of how you're going to get there. And this is where the statistics helps, because you've got some vocabulary you can put together and say, oh, I know that these algorithms do this, this, and this, and I know we've got this data. So hopefully we can get some value by putting the two together. Anyway, so this is actually to highlight some personality types who I think would best suit sort of a machine learning role. But machine learning is not a one-man job either. It does normally take the expertise of a few people, so that is something to consider. Don't get me wrong, I do a lot of this stuff as best I can on my own, but a lot of the time you do need some input from other people who have a broader scope, I suppose, than you do in other areas of data and the business. So that was just some way that I was trying to highlight where people might fit into that. I won't run through the trends so much. These are from February. It was just highlighting how poorly the UK are doing in terms of machine learning in the public domain. We don't do particularly well, but the places that you'd expect to do extremely well are doing extremely well. USA, not particularly, and that is partially to do with political things, but I won't bother getting into that. A few things that I do want to point out is the Netherlands is doing quite well with AI. It is an awesome tech hub. If any of you have been to Amsterdam and seen some of the museums, for example, a lot of them have integrated a lot of really awesome tech. Facial recognition. There's loads of machine learning going on in the streets, on traffic lights, in cars. It is one of, I think, Europe's best hotspots to see machine learning in action, or at least the results of it. Anyway, the results of all of those uses pictures at this point were, there's a huge hype around AI. It is investor candy at the minute, which is what we help loads of companies do, is to find ingenious ways of utilizing machine learning and artificial intelligence, because there are a lot of grants at the minute that help companies in sort of R&D for that. Anyway, there's currently a very poor capability to meet expectations. All solutions are in their infancy, and there's a huge gap in the dev market too. Companies aren't sure how to use machine learning and what value they can get back, or even what a machine learning dev CV would look like. And going back to that, these guys are all perfectly suitable for machine learning roles. So to highlight your CV to be more sort of data centered is an art, I suppose. But unless your employer understands it, they're not going to see the value that you can bring. Anyway, so one thing I did want to highlight is that lots of devs don't understand that they are perfectly suitable for machine learning, and there's a huge shortage of machine learning devs. And an even bigger problem is academia is sort of, the technologies that I'll introduce you to next will be what I suppose is introduced to students in universities or in academies, for example, because it's all based in Python, which is a very, very easy language to pick up, I think. It's very verbose, and lots of academics use it. And as a result, there's a huge ecosystem of tools to help people with absolutely zero coding knowledge whatsoever to get started immediately. The trouble is with that, you have the academics who have almost no practical coding experience, building libraries, and sometimes it takes a few years for the new innovations, I suppose, in algorithms and stuff to sort of trickle down into the enterprise. So a lot of the packages that we have available to us now are years old and don't contain the most recent and most effective programs, which is a bit of a shame. But hopefully, with a bit more awareness, people can start closing their gap a little bit. Okay, so I won't bother going into this, but I suppose that there are some things that are worth mentioning. So typical personality traits for machine learning. If you have a STEM degree, then you're on the right track, I suppose. Maths is useful. So the more familiar you are with mathematical concepts, the more creative you're able to be or get, I suppose. The trouble is with machine learning, the solutions that we have available to enterprises, like the really common, popular ones, the really big sort of Amazon, what's it called? Oh my God, sorry, I'm drawing a blank. Anyway, a lot of the big ones are built for, I suppose, a much higher level engineer, should I say. But to get the real value out of your data, you need to be quite granular, and you need to be very, very custom about how you do things, because everyone's data is custom. Unless you are running WordPress and have been for the last 50 years or 20 years, there's no one product that is going to fit your needs. And in fact, there is nothing for WordPress at this point, because never mind. Anyway, so I suppose what I wanted to highlight here is data engineers, for example, are interested in the how rather than the why, and data scientists are more interested in the why and rather than the how things are done. There is a good mix that can be had, I suppose, from a really, really small team that could be really quite effective. If you have data in a good shape, which makes all the difference. If you don't prep your data, you will get absolutely terrible results. So that's where data engineers come in handy really, really well. Okay, so suitable for technologies for machine learning. There's language considerations, OSI layer considerations, which I don't think I'll go too much into today. And then frameworks for enterprise. Those are, I suppose, the three massive considerations, obviously aside from the people, which are the team. Okay, so there's actually one more that I wanted to add to this one. But anyway, so Python is I suppose, the broadest because it has so many packages. There's 12,000 plus packages for Python and data science and machine learning and all sorts. Some of them are really, really small, but they do such an important job. So it's a bit like, I suppose, the end of line delimiter that we have used in almost half of all the NPM packages. It is one of those things. But Python is by far the most used language for data science, and that's because it's really easy to pick up, and the academics are encouraged to, and are almost force-fed that in university, unfortunately. Anyway, R is extremely fast. You'd find that running on graphics cards, for example, but it's really good for data visualization, and data science is, well, 1/3 of data science is the visualization of it. If you can't communicate your results, then they're totally worthless. Julia is, well, was or still, I suppose, is my favorite. It's LLVM compiled, so it means it can run on absolutely almost bloody anything. And it's super efficient. It has a really, really modular compiler. So you do get huge performance gains, especially if you're looking at crunching an enterprise's data that's been around for 50 years, let's say, and has, stupid amounts of data. Julia can really help you shave off, honestly, every millisecond you can shave off a single query ends up amounting to days or weeks or even months in some cases when building or training your data. Go has lost my favor since I've written this for reasons I won't bother going into. But with more complex operations, Go is a really easy language to pick up to begin with, and it's very, very low level and very, very fast. The trouble is when you start needing to get more granular and start needing more strict types, Go, I think, falls short and becomes more difficult to use when you need to do more granular things. PHP 7, yeah, I would say it's still controversial. I love PHP, so I thought I'd stick it in there. There are some really cool packages. So if you're from a web development background, I can share with you some resources that can help you get started with statistics and data science without having to go too far out of your comfort zone, for example, to start playing with things. Java and Scala, I put them in the same thing because they both run on the Java virtual machine. The bonus of that is that you have access to a huge wealth of static data types, so which is the issue with Golang. Anyway, so it's not beginner friendly, unfortunately, or easy maintainable. And in the long run, if you have huge data sets, you're going to suffer a little bit because the Java virtual machine isn't exactly all that performant. Anyway, C# is down there as well, just because I think everyone at some point has probably had some exposure to it. It is very good. It is very, very fast as well. You have access to memory management tools, which is fantastic. The one last thing I wanted to add into this list was actually Swift, which has been recently, people have been using it more and more for machine learning, and it turns out to be an extremely performant language indeed. Unfortunately, you do have to write it in a particular way that does make it uglier and less maintainable. But if you only do that in certain places where you know that you will produce, I suppose, lag or poor latency, then Swift is actually a really cool option. So if you do iOS development, for example, which I think is technically it's a general purpose language, I use it for writing iOS apps at the minute. And technically, it's a general all-purpose language that can run almost anywhere. But I've only seen iOS developers use it. But that is, if that's what you're familiar with, then there aren't that many resources yet for machine learning for Swift. But it is definitely well on its way to becoming that. I think Google have now adopted it and have started to put loads and loads of resources into making Swift the new machine learning language. So that's something to keep your eyes open for, I suppose. Python popularity. This is from February. It is very popular. I'll just end with that. Anyway, so useful Python libraries. So there's data analysis, there's the visualization, and there's the machine learning, and that's ultimately what makes anything useful in machine learning. You need to be able to visualize your data to communicate your results. You need some really awesome data analysis tools, and this is where NumPy, SciPy, and Pandas come in handy. The cool thing about Pandas, for example, is if you're used to working with relational databases, for example, you're used to seeing tables and stuff like that. However, plucking, I don't know how else to put that, that's a sort of Laravel or Doctrine ORM terminology, I suppose, but to pluck columns or bits and pieces of data sets, or to build matrices, for example, doesn't come very naturally. We normally think in row by row or column by column kind of thing, but Pandas make it easy to build matrices. If you don't know what a matrix is, then it's essentially a table. But you can do really cool stuff with matrices. You can multiply, or you can sort of stack 5 or 6 matrices, and all for different purposes, all for different reasons. But for example, matrices are something I think everyone probably has had something to do with at some point, probably in their GCSE levels. But if you didn't continue with statistics, you probably haven't had much to do with them. but they do come yeah, they do come in handy a lot in data science. A lot of the time, you're comparing not just two dimensions. So a typical matrix is a table, a flat table with an x and a y axis. But for example, we can probably only visualize a three-dimensional matrix, right? Like a Rubik's Cube, for example. But in maths, you can express anything to have as well an infinite number of dimensions, for example. So if you've got hundreds of attributes, those are all each a dimension. Some are fixed, some might be variable, but that's where the machine learning comes in handy. You're trying to identify what needs to be variable or what you can make variable to affect other things, for example. So having a decent background in some core maths will help you visualize things in future, or as I was saying, get more creative with your data. Every attribute essentially typically can be seen as an entirely new dimension. So what we can't visualize in 3D, we can only do in maths as an expression. And that's where you'll need to be able to get a bit more creative with your stuff to get really granular, really more relevant results, should I say. Anyway, OSI layers, I was just going to highlight basically that these are actually two images highlighting the same thing, just with different words, which I thought might appeal to people who have different exposures. But ultimately, why I wanted to point this out was we deal a lot with packets, especially if you're dealing with an enterprise environment. Whoops. You'll end up you'll have access to absolutely everything virtually, right, through IP addresses and databases and stuff like that. And this is where RTC comes in handy. So real-time communications comes in handy to reduce the latency, the hop between making a request for data and getting the data back. Oftentimes you're looking at petabytes of data, which will take days or weeks. And if you haven't got as low latency as possible, you could wait for weeks when you only have to wait for days, for example. So this is where WebSockets are awesome. So I think every language technically has some support or a wrapper. Even PHP, for example, has a wrapper for ratchets, I think it's called, which gives you access to the C-type binaries for WebSockets, which shaves off your time. Rather than using TCP and UDP over HTTP, you can use WebSockets instead, or SSH or something, which has enormous benefits for performance. Anyway, so enterprise stack options. Apache Spark, you guys have probably come across this at some point if you've had any interest in data science. That isn't just strictly speaking necessary or useful for machine learning. It has a huge range of other applications also with real-time communications, funny enough. And that's because I suppose it's purpose-built for rapid streaming and queuing. So any real-time communications will be using some version of Spark, whether or not they know it. Hadoop is slightly different, and that's because you can assign clusters to do certain jobs. So that way you can maintain certain clusters that do only one job. So you can make them, for example, if you write an application in R, so graphics type memory, super quick. But for example, if you give that only a very, very specific job or a type of processing, you could really make your clusters or your setup a lot more efficient. Again, shaving days off latency, for example, through training your algorithms. All this adds up. Anyway, so Microsoft Azure, AWS, and Google Cloud Compute offer their own versions or their own tools, I suppose, to help you with machine learning. To get you up and running in no time, as they claim, and the chances are you can get up and running and get very little value back, in my opinion. As I was saying, you need to have a really deep understanding of what you're trying to do, your data, and what you think you might be able to achieve with it. So a lot of the exploration is just actually exploring your own data and knowing what you've got. Anyway, so Amazon SageMaker is apparently a fully managed cloud deployment environment, automatic data labeling. So that helps with supervised learning and semi-supervised learning, which we'll touch on in the next few minutes. Sorry, I'm just conscious of time. I don't know how long I've rambled for. I think, okay, I'm going to try and rush through these to give you guys some context, and then, yeah. Okay, so Types of machine learning: supervised, semi-supervised, unsupervised, and reinforcement. Supervised, let's just jump straight into it. Okay, so you need to know enough about your data and their types. Again, super important because you can treat types if you think about them as sort of having attributes, or you can attach functions to certain data types, so their abilities become inherent. It does make crunching a lot quicker. Anyway, so never mind that. Have an expectation of what the outcome might or should be. So this is, I suppose, the simplest form of machine learning, and in many cases is not even considered to be machine learning because the algorithms that you'd use would be, I suppose, the most basic and can be expressed in a linear function, so an extremely simple linear function. So you could almost argue that it is not machine learning. However, yeah, I'll run through a really poor example, which is, right, so this app, I suppose, your weather app, or telling how long it'll take for you to get home. So you've got, in this example, you've got time of day, which is, I suppose that could be variable, whether or not it's a holiday, so a Boolean, I guess, and the weather. So if we've got 3 fixed variables and we've got 1, I suppose, unknown that we would like to know, based on all data we've got, historical records of how people behave and how they drive and how they do this, that, and the other, on holidays and the time of days, so rush hour, lunchtime, stuff like that, we can come up with an accurate-ish commute time for you to get home, depending on what time of day it is. And the weather, and if it's holiday or not. So that's a really awful example of one, but it's the simplest one to understand because everyone has a weather app on their cell phones. Okay, so unsupervised learning, which I think is a lot more fun. This is a lot of trial and error stuff. And oftentimes you have no labeled data. So labeled data just means you've earmarked data or data types, and you said, right, I understand that this has relationship to that, and this has relationship to that. So that's tagging data. That is declaring it as a known variable, or you know what value it brings. So you're almost watching it. So if you're debugging, you could say you're watching that as a variable. So you can earmark or tag as many data bits as you like, which will then build a picture for you. And then everything else sort of becomes a picture behind it. So you're almost selecting like your first row of troops, and then everything else that follows behind it is will build a picture for classification, for example. Actually, that was the next point. So you can use different algorithms to form connections by observation of data. So as long as you have a few labeled bits of data, or if you have it totally unlabeled, you can just say, let's just crunch it using these 3, 4, 5 algorithms. Each can be on a separate thread, so you get 5 different results. You might build pictures and say, okay, right, that looks like this looks like this. It can start automatically classifying your data for you. It won't know what it is that it's classifying or why it looks like it does, but that's for you to know. That's for you to apply the meaning to the objects you get back. So for example, all right, so we did some used behavioral mapping or clustering in the health industry recently, and the idea was we were trying to help people get back to work after having a traumatic experience. So this is sort of PTSD type stuff. Lost limbs were or patients with lost limbs were our sort of target audience, I suppose. So we had a VR application built, and users would sit there and sort of go through this course, I suppose, and we would pick up sort of their heart rates, certain hormones that they sweat at certain intervals, and we would try and map the content back to the overall user experience. So people really enjoyed it and said, oh, you know what, actually, I did not feel any chronic pain or any pain. Chronic pain is only chronic after 28 days. It becomes a mind thing. And part of this VR course is to try and help people get out of chronic pain. So to break that cycle, you need another 28 days to exit, I suppose. And we were trying to map what content worked for what users, because people respond to differently to different stimuli. So we could build sort of profiles or personalization or personal profiles, I suppose, almost, and we could say, right, okay, this user looks like this other user in terms of data. We don't know what that data is or was. We haven't labeled anything, but we know that this object looks or matches this object. So maybe the same content will work or will have similar effects to this user as it did for this user because they look similar in terms of the data we've collected on them. And turns out in that particular case there was, or correlation did mean causation. That is also, I suppose, the first rule of machine learning. Correlation does not mean causation all the time. Just because fuel is £1 per litre, I wish it was still, near the motorways doesn't necessarily mean that on every motorway it's, I'll just leave it there. Correlation does not mean causation all the time. Okay, semi-supervised learning is when you've got a mixture of tagged and untagged data. What I was explaining before about earmarking certain data, that I suppose is semi-supervised. So when you have an expectation to some degree of what you're looking for, but you don't know what the rest is. So with the unsupervised learning, we just knew we had content, and this is different media. So it's rich media. It could be just audio, it could be just visual, it could be a mixture of both. It could be haptic as well for haptic feedback. But we could not almost be bothered to go through each type of data stream and tag certain attributes. All that needed to be totally implied. So we labeled absolutely nothing. But we knew to some degree what we would expect to see. Whereas in semi-supervised learning, maybe it's useful for you to know a few things. So you can find patterns behind what you already expect to see, and then it's what's behind, I suppose, that almost means more than what you've marked. So when you initially classify things or initially declare things as being A, B, C, D, E, it's what the data looks like behind those initial classifications that really make the difference, should I say. So for example, I suppose one of the projects that we've got going on at the minute is a civil engineering company, and it was to detect faults and warn engineers when there was a need to go fix something. So I suppose this is a rail station. They've got pumps. They pump sewage out of the carriages. Yay! And when those break, nobody wants to fix them. Funny enough, but there are certain things that I suppose for preventative maintenance to help the company or the maintenance company not have to send out somebody who's going to cost them £20,000 for the day. An early warning system would be useful. So we pick up loads of inputs. This is just a snapshot of the top sort of left corner. But there's about 20 or 40 inputs coming from these pumps. But the trouble is, every setup is different. Every rail station is different. And for example, the lengths in pipes or the diameter or the material used or the parts in the pumps mean different pressures, different temperatures, different wear. Everything's bloody variable. So there's nothing fixed that we could say, or with any guarantee that this setup is going to be the same absolutely everywhere. So this is where semi-supervised learning comes in handy. We know very few things about the setup. We say, right, okay, we know that they've got this much length of piping installed. They've got 3 pumps running, and these are the engines that pumps 1 and 2 use, and that's the engine that pump 3 uses, for example. But when we don't pick up a fault, for example, every second we take readings from these sensors, and for us to be able to figure out what a fault even looks like on a bespoke setup, we need to know on that bespoke setup what a fault looks like. So when there is a fault, somebody says, right, okay, there was a fault right now, it happened. They send us 5 minutes worth of data leading up to the moment of the fault. So that way we build our own models of what the data looks like when there is a fault and what the data looks like for a few minutes before the fault. So we can then say, oh, right, okay, well, we can see that the temperature was building rapidly for the last 5 seconds before it cut out because the fuse blew or something. We can start learning to identify what things look like, what the environment looks like before something happens. to then thwart it. So we can start putting automatic triggers, say, okay, well, if this is happening, then reduce the pressure and just ring the bell and say, right, that there's a blockage. So temperature's going up, there's suction's on max, and there's no flow. So stuff like that. That is semi-supervised learning. So as we get more and more data, more faults for each installation, that then retrains the model to then say, right, next time we see this sort of data, we know that there's going to be a fault imminently, or this is how we build the early warning system. So I thought that was a good example to demonstrate what semi-supervised learning looks like and how it can bring you value. Okay, so reinforcement learning is literally what I just said, semi-supervised. Okay, so quality and efficiency from the basis or incentive for a machine to modify its own behavior. So what I was saying about modifying its own algorithm, retraining itself. You have weights, I suppose. Those weights you can modify on the fly. So that changes the results of exactly the same data going through it. Might look totally different after it's run through it itself and re-weighted the algorithm. Anyway, this is really good for sort of progressive stuff. So let's say we start a new event like today, this Megabites stuff. We can start tracking how many users pitch up. Oh my God, it's 1:15. I apologize, guys. I'll wrap this up. Okay, I'm going to have to skip this one. I'm sorry, guys. So reward-based just means that if the algorithm gets it right, we give it a token of, yes, you've done right. So whatever the state of that algorithm was, the state of the data, then becomes attributed to a positive. If we don't like what it comes out with, we can say, oh, no, and we deduct a point, or we punish the algorithm, I suppose. Then it knows that what it got through its state of the algorithm and state of the data wasn't what we were expecting. So maybe it will discard, not discard it, but know that any other data that looks like that might not be, strictly speaking, necessary to modify the weights in your algorithm. So that's how you can train an algorithm to train itself effectively, which is fun and really cool. I did have an example, a small game, little paddles and a ball going between the paddles, and you have to block your goal kind of thing. And if you reward the system for blocking or for not allowing any balls into its goal, it starts knowing, okay, I better block this ball then. But if we reward it more for getting that ball into the opponent's goal, weird, wonderful things happen. And it'll bend the rules as much as you like. We saw the paddle grow the full length of the goal to block any entry points whatsoever, which was a way of the game responding. Which is a way of the application responding based on the rules that we've given it. So unless you explicitly define a set of rules that it has to abide by, you'll find computers can be extremely creative as well. So that's really cool. This is like Skynet stuff. Anyway, so I had a bunch of resources. I only managed to get 2 on here, but I will put loads more, most likely on Python. I'm not peddling Python at all whatsoever. I actually do most of my machine learning in Bash, but I will. I think it's the best route to get started, because that's where everyone else gets started. That's where students, that's where universities and collaborators, I suppose, get started, is with Python and with notebooks. What are they called? Jupyter notebooks. You can have inline code, you write expressions, and it will literally process your data or pass your data. If you have CSVs coupled with it, you can start playing with data immediately. So I will put those in, and I'll send that over to Luke and on LinkedIn or something, so everyone can have access to that. Yeah, I think that's it. I apologize. I ran over double the time. I did not see the 2 hands, Luke. I apologize. So yeah, I guess that's me. If there are any questions, then let me know.